A very important concept in the field of chemical kinetics is called the rate law. The rate law shows the mathematical dependence of the reaction rate on the concentrations of reactants. Now remember our representation of a generic chemical reaction where we had reactants A and B with coefficients small a and small b reacting by some reaction mechanism to form products C and D, C having coefficient small c and D having coefficient small d when the equation is balanced. Now, as we said, the rate law is rate of the reaction as a function of the concentration of the reactants. So for our generic reaction, the rate law would take the following form. We'd say the rate, meaning the rate of the reaction, is equal to some constant K times the concentration of A raised to some power times the concentration of B raised to some power. Let's define these terms a little more explicitly. The reaction rate, as you recall, is usually in units of molar per second. It's change in some quantity per unit time. The rate constant is a quantity whose units will depend on the values of m and n. The bracketed A and B terms are the molar concentrations of the reactants A and B. Remember, the square brackets typically mean molar concentration. And the powers m and n are respectively the order with respect to reactant A, that would be what m is, and n would be the order with respect to reactant B. Another way of saying that is m is the order of the reaction with respect to reactant A, and n is the order of the reaction with respect to reactant B. The sum of those two terms, m and n, are typically referred to as the overall reaction order. Something very important to note here is that m and n do not depend on the reaction coefficients A and B. That's why we don't have A here instead of an m for the reactant A and B here instead of n for the reactant B. These exponents here, or powers, have to be determined experimentally, and what they are actually depends on what the reaction mechanism is. So again, the rate law is rate as a function of concentration, where these exponents here are not the coefficients of the balanced equation. They could be coincidentally, but they're not derived from those coefficients. We have to determine these experimentally. Here's some examples of experimentally determined rate laws. For example, here's a reaction of N2O5 decomposing into NO2 and oxygen. There's the balanced equation. The experimentally determined rate law for this reaction is rate equals the rate constant times the concentration of N2O5 to the first power. There's a 1 exponent 1 there. Note it's to the first power even though the coefficient in front of N2O5 in the balanced equation is 2. We say this reaction is first order in N2O5 because of the 1 here, the exponent 1, and first order overall. Here's another example of a reaction where all the coefficients in the balanced equation are 1. It's a reaction of an ammonium ion with nitrite ion to form nitrogen and water. Excuse me, there is a 2 in front of the water. The rate law here, experimentally determined, is rate equals K times the concentration of ammonium ion to the first power times the concentration of nitrite ion to the first power. So we'd say this reaction is first order in ammonium ion, first order in nitrite ion, and second order overall. And finally, here's a rather strange reaction of chloroform with chlorine to form carbon tetrachloride and hydrochloric acid. And what I mean by strange is that the rate law looks strange. The rate here is equal to the rate constant times the chloroform concentration to the first power times the chlorine concentration to the half power. So we'd say this reaction is first order in chloroform, half order in chlorine, and 1.5 order overall. Because remember, the overall reaction order is simply the sum of the exponents on these reactant concentrations. 1 plus a half would be 1.5. Now notice up here I had a couple of asterisks, and we want to point something out here, that in many reactions, the reaction orders are positive integers such as 1 or 2. However, fractional reaction orders are not uncommon, for example, this reaction here. In addition, we sometimes see a reaction order of 0, no dependence on reactant concentration, or even negative reaction orders, where the reaction rate decreases with increasing reactant concentrations. We'll look at zero-order reactions, but we'll stay away from negative reaction orders in this course. Well, let's spend a couple of minutes talking about the units for the rate constant K, because we said that it'll depend on the overall reaction order and, of course, on the units chosen for rate. I have a little footnote here, and you want to recall from a previous lecture that rate could be expressed in several different ways. Most commonly, we refer to reaction rate as molar per second, but there's no reason that rate could not be expressed some other way. For example, molar per hour. It's still a change in quantity over a change in time, or atmospheres per second if you were following a reaction involving gases. For this lecture, we will talk exclusively about rate in terms of molar per second. So let's use the 3 rate laws from the previous slide to illustrate how we might come up with the proper units for the rate constant. The first rate law was rate equals K times the first power N2O5 concentration to the first power. I've made the K red here just to emphasize that we're looking at the units for K. And recall the units for rate are molar per second, and the units for N2O5 concentration would be molar. So I'm simply going to solve for K, and we'll see what the units come out to be. If I divide both sides by M, I'd get rid of the M on the right, and we just have K, and we'd have molar per second divided by molar. And of course, that is the same thing as molar per second times 1 over molar. You can see the units molar cancel, and we'd be left with units of 1 over seconds for K. And typically 1 over seconds is designated as seconds to the minus 1. So for an overall first order reaction, the rate constant K has units of per second, 1 over seconds per second, or sometimes called reciprocal seconds, or just seconds to the minus 1. For the second reaction on the previous slide, we said the experimentally determined rate law was rate equals K times ammonium ion concentration to the first power times nitrite concentration, I think that should be a minus there, to the first power. And so the units would work out. For example, rate is molar per second. Each of these concentrations are molar concentrations, both raised to the first power. So basically we have molar per second equals K times molar squared. If we divide both sides by M squared, we'd isolate K, and we'd have M over S divided by M squared, which of course is the same thing as molar per second times 1 over M squared. One of the M's cancel, and we'd have 1 over seconds times M. And we would write that typically as m to the minus 1 times s to the minus 1. So for an overall second order reaction, the rate constant K has units of per molar per second. May sound strange, but that's how it's typically said. And algebraically, you can see how we express that. Let's look at the final reaction from the previous slide where we said rate equals the rate constant times the chloroform concentration of the first power times chlorine concentration of the half power. Again, the units for rate are molar per second. The units for the chloroform would be m, because it's m to the first power. For chlorine, m to the half power. So basically we have molar per second equals K times m to the 3/2 power. I'm going to divide both sides by m to the 3/2, which is the same thing as molar per second times 1 over m to the 3/2 power. And m would cancel out here, leaving just m to the half power here. And we could then write this as 1 over s to the m, s times m to the half power. And we could write that as m to the minus 1/2 s to the minus 1 for units of K. And so for an overall 1.5 order reaction, the rate constant K has units of per square root molar per second. Again, what we did was we found units using a little algebra, but the important point here is the actual units for the rate constant will depend on what the rate law is. The rate is always molar per second. These concentrations will be in units of molarity, but it's the powers on these that we determine experimentally that will ultimately determine the units for K. Typically, a rate law is found by an experimental technique called the method of initial rates. And in the method of initial rates, several reactions are performed, and what you do is determine the reaction orders by observing how the initial rates of these reactions change as you systematically vary the starting or initial reactant concentrations. Recall, as discussed in a previous lecture, the initial rate is technically the instantaneous rate at time equals 0. Since, of course, this is rather impractical to measure, the initial rate is typically taken as the average rate over the first 10% or less of the total reaction time. Now, the determination of reaction orders from initial rate data, this is actual data that you would obtain, is often very straightforward. Let's look at this reaction, which is the reaction of NO with chlorine to form NOCl. The coefficients are 2, 1, and 2 in the balanced equation. And we can construct a rate law expression, at least a starting expression, using the concentration of reactants. So what we have here is we say the rate of the reaction is equal to a rate constant times the concentration of NO, one of the reactants, raised to some power that we're going to figure out, times the concentration of chlorine raised to some power that we're going to figure out using the method of initial rates. So our task is to determine M and N and ultimately K by going to the lab and measuring the initial rates of the reaction as we systematically vary the initial concentrations of each reactant. We'll often symbolize initial concentration as square brackets with a subscript 0. So here's a table of data where 3 experiments have been done. Experiment 1, Experiment 2, Experiment 3. Let's look at Experiment 1. In Experiment 1, if the initial or starting concentration of NO is 0.1 molar, and the initial or starting concentration of chlorine is 0.1 molar, the initial rate is measured to be 0.18 molar per second. So you'd have to go in the lab, find some way to observe this reaction and time it and so forth. Look at the average rate over the first 10% of the reaction and calculate a reaction rate, an initial rate. In experiment 2, what's done is that the concentration of NO is kept the same, but the concentration of chlorine is doubled. And that's what we mean by a systematic variation in reactant concentrations. And when we do that, we see that the initial rate doubles. Now that automatically should tell you something about how the reaction rate depends on the concentration of chlorine in the rate law. We'll come back to that. In experiment 3, we have increased the concentration of NO to 0.2, but kept the chlorine concentration at 0.2. So between experiments 2 and 3, we've only changed one thing. We've changed NO. We've doubled it. And the rate here goes from 0.36 to 1.44, which is actually a factor of 4 increase, even though we only doubled the concentration of NO. And that should also tell you something about the coefficient M. Basically, the coefficient M is going to be 2, because again, when you double the NO concentration from 0.1 to 0.2, while keeping the chlorine constant, the initial rate quadruples, which means there's a squared dependence on NO. And N will turn out to be 1, because when you double the chlorine concentration while keeping NO constant, the rate doubles, which means that this power here must be 1. Therefore, the rate law for this reaction would be rate equals K times NO squared times the chlorine concentration. So we'd say this reaction is second order in NO and first order in chlorine and third order 2 plus 1 overall. Well, one thing that you might ask right now, even if you didn't quite follow how I got 2 and 1 here, you might object to the entire process, because remember back in a previous slide, we said that these reaction orders, M and N, are not the coefficients in the balanced equation, yet we just solved a problem here or looked at experimental data where the reaction orders did come out to be exactly the coefficients in this balanced equation. So what gives? Well, here it's probably just a coincidence. Now, let's determine K, including the units, because if we want the complete rate law, we would want the actual number value of K and the correct units. So here's our reaction, here's our rate law, and we've determined these reaction orders, and I've highlighted K in blue here because now we want to determine K. One thing you want to remember, or at least be aware of, is that rate constants change with temperature changes. So although we didn't state a temperature for this reaction, we will assume that in this example that whatever the temperature was, it stayed constant for all 3 experiments. You'll typically see a temperature given in problems involving kinetics, so that it's understood that the temperature is not changing, or later it's understood that the temperature is changing for a certain reason. But if you want the rate constant to be a constant, you need to state the temperature, because the rate constant will change with changing temperature. Okay, so here's the experimental data from the previous slide reproduced here, and we've added another column that we're calling rate constant. And since the reaction orders M and N have already been determined, we can use the initial rate data to calculate 3 rate constants, 1 for each experiment. And let me show you how here. So let's calculate K from experiment 1. So the rate from experiment 1, which we'll call rate 1, that would be the 0.18 here, we know is equal to K times NO squared times chlorine. So we can solve for K, and that would be the rate, initial rate 1, divided by NO concentration squared times chlorine concentration. And we have all that information here in experiment 1. We just substitute the data. Rate 1 is 0.18 molar per second. It's right here. The concentration in experiment 1 for NO is 0.1 molar, and you need to remember to square it because M is 2. And the concentration of chlorine is 0.1 molar, and that's to the first power. If we just solve this, we end up with 0.18 over 0.0010, and the units would be molar per second divided by molar cubed. So the number turns out to be 1.8 times 10 squared, and the units turn out to be m to the minus 2, s to the minus 1. And what we'll do is put that right up here in the rate constant column for experiment 1. Now likewise for experiments 2 and 3, we can determine the rate constants in a similar way. For experiment 2, we'd have the rate of experiment 2, which would be 0.36, divided by the concentration of NO, which is 0.1, and we square it, times the concentration of chlorine in experiment 2, 0.2 to the first power, and we end up with 1.8 times 10 to the second molar m to the minus 2, s to the minus 1, and we've written it right here. And likewise for experiment 3, using the rate data and the concentrations from experiment 3, we again get 1.8 times 10 squared for the rate constant. So the rate constant is a constant. Doesn't that make sense? Well, yes, it does. The rate constant should be a constant. We should get the same number for each of these experiments. However, in the real world, real data is subject to some uncertainty. And so we're going to deal with that in just a second. But for now, we have a complete rate law for this reaction. Rate equals 1.8 times 10 squared, m to the minus 2, s to the minus 1, times the concentration of NO squared times the concentration of chlorine to the first power. We've determined the rate law for this reaction. We've determined how rate depends on the concentrations of the reactants. So on the next slide, we can use this rate law. We can use it to predict how the reaction rate, what the reaction rate would be for any reactant combination. I should say any reactant concentrations. So I've rewritten the reaction here, 2NO plus chlorine going to 2NOCl. And over the arrow, I've written the rate constant that we've determined for this reaction. In general chemistry textbooks, you'll rarely see the rate constants drawn over these arrows. We will in later lectures in this module. But this is typically done in the research literature to remind folks that a rate constant has been determined and what it is at a specific temperature. So here's a question we can answer now that we've determined the rate law. Suppose someone asks, what would be the rate of this reaction when the NO concentration is 0.667 molar and the chlorine concentration is 0.039 molar? Well, this is pretty straightforward. Because we have the rate law, we can simply substitute in the concentrations of NO and chlorine and solve for a rate. So we do that here, and remember we have to square the concentration of NO because that's what the rate law tells us. And we end up with a rate of 3.1 molar per second. Remember, the rate has to come out in molar per second. And when you take the rate constant units and multiply by the units from the reactants, which would be m cubed here, we do get molar per second, and the rate turns out to be 3.1 molar per second. Now let's revisit the method of initial rates. And remember I mentioned a few seconds ago that real data is probably not as easy to work with or as straightforward as made-up data. And so we're going to try to revisit this reaction and some experimental data and make it look a little more realistic. So remember the reaction and the initial rate law form before we knew what the rate law was. If we didn't know what it was, of course, we'd write it this way in a general form. And remember, we want to determine M and N and K. Now, previously, when we did this, we had a table of 3 reactions, 3 experiments, and we determined M and N, or I did, by what we call inspection, meaning we just looked at how the initial rates changed with systematic changes in initial concentrations. And because the data was so straightforward, it made it easy to determine that there was a squared dependence here for M and a first order dependence for N. Now the data below in this table make determining reaction orders by inspection a little bit more challenging. For example, let's suppose we want to compare experiments 1 and 2, where the chlorine concentration doubles and the NO concentration stays the same, just as in the previous table. Well, let's suppose the initial rate measured for experiment 1 was 0.159 and the experimental initial rate for reaction 2 or experiment 2 was 0.371. Well, previously we said, oh, this is easy. When the chlorine concentration doubled, the reaction rate doubled. Well, here it doesn't double exactly. If you take 0.371 and divide by 0.159, the rate goes up by a factor of 2.3, not 2. So, and we'd find a similar complication when in comparing experiments 2 and 3. So we can still use the method of initial rates, but we need to be a little bit more careful in our approach. So what I'd like to do is walk you through a more systematic approach to determine the reaction orders M and N when it's not obvious by inspection necessarily what M and N should be. So let's put our reaction and rate law expression, a general one, and our data from the previous slide up here. And our first job would be to determine M. And what we'll do here is, as we did before by inspection, we need to compare 2 experiments where the NO concentration changes while the chlorine concentration stays constant. That would be experiments 2 and 3. We want to find out the dependence of NO, a dependence of rate on NO, so we're determining M. So we're going to change NO and leave chlorine constant. Well, this will sound strange, but what we're going to do is divide what we call the rate expression for experiment 3 by the rate expression for experiment 2. To do that, we need to come up with rate expressions for experiment 3 and experiment 2, and this is straightforward. What we mean by the rate expression for experiment 3 is just the rate law in terms of experiment 3. So in other words, we have a rate determined in experiment 3 of 1.41 molar per second equal to a rate constant times the concentration of NO, which is 0.2 in experiment 3 raised to some power m, times the concentration of chlorine in experiment 3 raised to some power n. That would be our rate expression for experiment number 3. Likewise, we can get a rate expression for experiment number 2. rate would be 0.371 equal to a rate constant times a concentration of NO, which is 0.1 molar raised to the M power, times a concentration of chlorine, 0.2 molar raised to the N power. And now we will literally divide the equation for the initial rate of experiment 3 by the equation for the initial rate from experiment 2. So here's the rate expression for experiment 3. Initial rate 3 equals 1.41 equals K times 0.2 to the M power times 0.2 to the N power. And we're going to divide by initial rate 2, which is 0.371, equal to K times 0.1 to the M power times 0.2 to the N power. This may look difficult, but it simplifies quite quickly. For example, the units here, molar per second, are on top of each other, so they cancel out. So all you're left with here is 1.41 divided by 0.371, which is 3.801 with no units. K cancels out, so we've gotten rid of that. And actually 0.2 molar to the N power is the same on top and bottom, so those whole terms cancel out. So all that's left is 0.2 molar to the M power over 0.1 molar to the M power equal to 3.801. And as I said, we've now successfully rid ourselves, for the time being at least, of the rate constant and the exponent n. We can concentrate on just solving for m. Now if you do a little algebra, you find out that 0.2 molar to the m divided by 0.1 molar to the m is the same thing as 0.2 molar to the m divided by 0.1 molar to the m, all raised to the m power. And this term in the brackets here just turns out to be 2 because units of molarity cancel, and 0.2 divided by 0.1 is 2. So what we literally have is 3.801 equal to 2 to the m power. If you think about that, it appears that m will be around 2. Now, not exactly 2, but close to 2, as we thought. But we can find a value quite precisely by doing a little more algebra. Let me show you how. What we can do is we can take the log, this would be log to the base 10, of both sides of the equation. And by the equation, I mean 3.801 equals 2 to the m. So we're going to take the log of 3.801 and set that equal to the log of 2 to the m power. We can do a little rearranging because the rules for logarithm tells us that we can take this exponent and put it right down in front of the log term. So what we have here is when we solve for m would be equal to the log of 3.801, which is 0.58, divided by the log of 2, which is 0.301. We would get a value of 1.93, or around 1.9, for the value of the exponent m. Well, let's proceed to find the exponent n in a similar way. What we need to do, as before, to find n is compare two experiments where chlorine changes and NO stays constant. That would be experiments 1 and 2. And we'll divide the rate expression for experiment 2 by the rate expression for experiment 1. The rate expression for experiment 2 would be the initial rate, 0.371, equal to K times 0.1 molar to the M power, there's 0.1 molar for NO, times 0.2 molar to the N power, 0.2 molar for chlorine. And likewise, the rate expression for experiment 1 would be 0.159 equal to K times 0.1 molar to the M power times 0.1 molar to the N power, getting the values off this experiment 1. And we're going to divide the equation for initial rate 2 by the equation for initial rate 1. And you can see, as before, that things drop out. So when you divide these two rates, of course, these units cancel, and you're just left with a number. The k's cancel on the right here, and this time the terms involving m cancel because they're the same on the top and the bottom. So what you're left with are the two terms involving n. This looks strangely similar to the last slide. One thing you might ask at this point, before we go on, is what would have happened if instead of dividing initial rate 2 by initial rate 1, in other words, having this expression on top and this one on the bottom, that we reversed it and we put the initial rate 1 on the top and initial rate 2 on the bottom. You'd still get the same answer for n as long as you did the algebra correctly. So the intermediate steps might look a little bit different, but in the end you'd get the same value for n. So let's continue to solve here. We can see that this equation turns into 2.33 being equal to 2 to the n power. And as you can see, n would be very close to 1, but again, we can get it more precisely. We'll take the log of both sides, bring the n down in front right here, and then solve for n. And we get a value for n of 1.22, or around 1.2. So now we can write a rate law and calculate the rate constant. Here's our reaction. Here's our generic rate law. And if m equals 1.9 and n equals 1.2, then technically the rate is equal to k times the NO concentration raised to the 1.9 power times the chlorine concentration raised to the 1.2 power. Now, it's common to round off reaction orders to the nearest whole or half integer. So in this case, we could say the rate is equal to k times NO to the second power times chlorine to the first power. This is identical to the rate law we determined with the more easily manipulated data earlier. Now let's solve for the rate constant for each one of these experiments. So I've added the rate constant column here, and we need, of course, to get the appropriate units for k. We can do that for experiment 1 by just solving this rate law for k. So here k is equal to the rate for experiment 1, 0.159 molar per second, divided by the concentration of NO for experiment 1 squared times the concentration of chlorine for experiment 1. And we get a rate constant of 1.59 times 10 squared, m to the minus 2, s to the minus 1. And following significant figure conventions, we can only use two significant figures. So I've rounded it off to 1.6 and put it in the table right here. Likewise, we can solve for the rate constant for experiment 2. And as you can see, we don't get exactly the same number using the data from experiment 2, but nonetheless, I've rounded off to two significant figures, and we get a rate constant there. And finally, for experiment 3, we can do the algebra and come up with a rate constant of 1.76 times 10 squared, which I've rounded off to 1.8. So you can see that the rate constant from experiment to experiment is not constant, which seems counterintuitive, but the rate constant should be constant. It's just that, remember, real data has some uncertainty in it. And so the rate constant determinations are going to have some uncertainty for each experiment. And for this case, what we would do is just report an average of the three rate constants. That's the value you would report for the experiment. So the complete rate law, as we found out before, was rate equals 1.8 times 10 squared, m to the minus 2, s to the minus 1, times NO squared times chlorine to the first power. So the reaction is overall third order. It's second order in NO, first order in chlorine.